Good afternoon. My name is Takiwa Smith, founder and executive director of Science, Engineering, and Mathematics Link Incorporated, also known as SCM Link, and I want to welcome you to our STEM in the City workshop. STEM in the City is a program of our Math and Science Career Academy whose focus is to expose youth to earth and environmental sciences. These are the sciences that, whether youth are aware of it or not, impact our everyday lives, from the quality of air, access to clean water, good soil. There are just so many things of earth and environmental sciences that you don't even think about, because STEM is really all around you and everywhere. And so the purpose of these workshops is to give you an opportunity to meet earth and environmental sciences, to learn what these fields are and what they do and how they impact our everyday lives, to learn the career paths of people that work and study in these fields, and most importantly, to give you an opportunity to see if this is something that you are interested in, because we need earth and environmental scientists in the future to continue to conserve, save our planet, to do research, to do build systems, and all of these things that make our quality of life well, and protect and conserve the planet that we lived in, so we continue to have food, clean water, and beautiful places to visit, right? On vacation, like our beaches and oceans. And I'm so thankful for earth and environmental science because I like crabs and they make sure that our oceans are clean or give us things that we can do. So without further ado, I'm going to introduce our programmer Carlin Pounders, who is going to introduce today's speaker.
Thank you, Takiwa. Hi, everyone. Thank you so much for joining us. Today's speaker is Danae L. Carlis, PhD, who is an award-winning meteorologist and serves as the Deputy Director at NOAA's Global Systems Laboratory, short, uh, otherwise known as GSL. Prior to GSL, Danae worked at the Weather Program Office in Washington, D.C., where he was the founding program manager of the Earth Prediction Innovation Center. Danae works between science, policy, and society. Danae attended the Mecca, Howard University in Washington, D.C., where he obtained a Bachelor's of Science degree in chemistry as well in 2000, as well as a master's in 2002 and PhD in 2007 in atmospheric sciences. In 2007, Danae was the second African American male to receive his PhD in atmospheric sciences from Howard University. In his spare time, Danae enjoys football, mentoring, and coaching students, and spending time with his family. So we are very lucky, and we have a wonderful presentation prepared for us. So without further ado, I will hand it over to Dr. Carlis.
Thank you so much, Carlin. I really appreciate the opportunity to be here and really just, share my story. Your mission at SimLink really is extremely important. I wish things like this were around when I was a young child. I probably would have known better of really what I wanted to do with my career. And Takiwa, thank you again for the opportunity to be one of your presenters. I know it's almost the end of the year, but hopefully we can have a little fun here today. I'm really excited to share my story and to share Science on a Sphere with everyone here. So this is a great opportunity. Thank you. I'm going to go ahead and share my screen here. So give me a second, because I want to go ahead and share kind of short presentation with you. And I'm going to take about 20 to 30 minutes to just kind of share my story. So I've titled this, STEM in the City, a world tour using NOAA's Science on a Sphere Explorer, which is a tool that we use at NOAA. And it's actually a tool that's used across the world. And so I want to share my story. And again, I'm the Deputy Director of NOAA's Global Systems Laboratory in Boulder, Colorado. I've been with NOAA for almost 19, a little bit over 19 years now. And so let me go to the next slide here. And so, how did I get started? So, I'm going to take you back to, when I was young, I was in high school. Um, I got my first job as a janitor, working in a insurance company, cleaning up their offices at the end of the day. I got a job working as a hardware salesman at Sears. And then when I got into college, I decided that I wanted to continue working after my freshman year of college. I started being a waiter at a restaurant called Houston's Restaurant in Washington, D.C. And so when you think back to, my education where I grew up, Tulsa, Oklahoma, I graduated from Booker T. Washington High School back in Tulsa. At the age of 16, I still remember that my mom asked me, what did I plan on doing when I graduated from high school? And the funny thing is that since I'm a first generation college student, I was a first generation college student, that I didn't really have a lot of influences with regards to college. The only thing I really knew about college was that it cost money. And, my mom said, what are you going to do, once you graduate? And I told her, I'll probably go out like the rest of my family members and, work, get a job, be a hardware salesman or something like that. And she thought that that was the dumbest idea that I've ever come out with. And she said to me, Danae, really, you have a really good GPA. You're really smart. You like school. You like learning new things. Why don't you think about going to college? And like, again, I told her, I said, Mom, the only thing I really know about college is that it costs a lot of money. And she was like, well, God will make a way. And so she said, go out and start applying for scholarships. And I applied for at least somewhere around 10 to 15 different scholarship programs out there. And by the time I was graduating, I had over $25,000 in scholarship money that actually helped me to pay for that first year of college at Howard University. And I decided that Howard was the place where I wanted to attend. It's a historically Black college in Washington, D.C. Again, I'm from Oklahoma, so going all the way to Washington, D.C. was a big move, right? And it was a big move because, number one, I wanted to see something else. I wanted to expand my horizons. I had, growing up in Oklahoma, I had pretty much only been to Oklahoma, Arkansas, Texas, places that really touched Oklahoma, maybe Missouri, places like that. And going out to Washington, D.C. was a big step for me. And, I thought it was a excellent opportunity, though, because going out to D.C., I got a chance to see so many people that looked like me, that was really focused on their education, that were, some of the most talented Black people in the entire country. And that's what I call Howard University. It is the Mecca for a reason, because we have some of the most talented African-American students in the entire country. And that, I wanted to be around that. And so I stayed at Howard, getting my bachelor's of science degree, continuing on and getting my master's degree. I did not pay a dime to get my master's or my PhD. So those of you that are in STEM, are thinking about STEM careers, you should not have to pay for a master's or a PhD. There are grants out there. There are professors out there that have funding that can support you to do that work. And I had no idea that this was the case. And so I continued on. And I want to just kind of talk about, after I graduated from Howard, I went to work as a research meteorologist. And so what does a day in the life of a research meteorologist look like, right? It's, you're logging into one of NOAA's supercomputers. These supercomputers are located in either West Virginia or Florida or someplace else. You're running a weather prediction model on these computers that have over 5,000 processors. You're also studying the performance of that computer simulation. And you're trying to find ways to improve those models, because those models are used as guidance for the forecasters that actually write up the forecast for you each and every day. And then, you talk about my day as a deputy director. Now, I don't actually work as a research meteorologist, but I have a lot of research meteorologists that work for the Global Systems Laboratory that I'm responsible for. And so my day really as a deputy director is very different than compared to when I was a research meteorologist. So I meet with the senior leadership team of GSL. We develop strategies and implementation plans. I go out and talk about GSL in presentations like I'm doing today. I also work on policies and implement policies that come from NOAA, the Department of Commerce, or from the White House. And so you look at how it started versus how it's going. It's very different. A lot of things happened in between the time when I was in high school, and that picture on the left is when I was in high school compared to me getting inducted into my high school's Hall of Fame here on the right, which was a fantastic honor. And so the journey, there's so many different things that kind of happen. Of course, growing up in Oklahoma, moved to Washington, D.C. Of course, I got to shout out my vice president, Kamala Harris, who is a graduate of Howard University, the Mecca, of course. And then I moved to Hawaii. I got a job within NOAA, and NOAA wanted me to move to Hawaii. And moving to Hawaii was a fantastic experience. My wife, my daughter, we all moved together back in 2004. And I was there in Hawaii for 3 years. Loved it, had a fantastic time. And then decided that I wanted to go back to DC. And so I went back to DC, worked there for close to 2007 to 2020. So 13 years, another 13 years of my life there in DC. And then in 2020, I decided that I was going to take an opportunity here in Boulder, Colorado. So I'm now in Boulder, Colorado. My office, you can see that picture on the right there, looks out on those mountains right there behind my office. So it's a pretty cool place to work. And now I want to transition to talking a little bit about NOAA. I don't know how many of you guys know what NOAA is. It stands for the National Oceanic and Atmospheric Administration. Our mission really is focused on science, service, and stewardship. I don't know if anyone out there can give me some comments with regards to what do you see in this picture? I can name a few things that you see. You see the ocean, you see people swimming in the ocean, you see a ship, right? You see airplanes, you see animals in the ocean. And if you could type in the chat, what are you seeing in this particular picture? You also see satellites. So you look at the NOAA mission, and the NOAA mission spans from the bottom of the ocean all the way to the surface of the sun. Our mission, we are monitoring both the bottom of the ocean and the sun. So that is really a broad mission. So a lot of work goes into doing that. So we have people that are in basically divers. We also have people that are part of our ships and basically drive our ships. We also have people that fly planes into hurricanes. And then finally, the folks that are developing our satellites. We hire a lot of engineers to develop satellites for us. And those satellites are used to monitor, and we'll talk more about this, they're used to monitor the pulse of the planet. And so you think about the NOAA mission, understand and predict changes in climate, weather, and oceans, share knowledge and information with others, conserve and manage our coastal and marine ecosystems. So that mission is really broad, but also very important to our daily lives here on the planet we call Earth. I call it the blue marble. Let's go to the next slide. So what does it mean to be a meteorologist? Now, most think that meteorologists, look up at the clouds each and every day. Some people think that meteorologists are chasing tornadoes each and every day. Most people, when I tell them that I'm a meteorologist, they say, "What channel are you on?" Danae, what channel are you on? I'm like, no, I'm not on anybody's channel. That's a form of meteorology, but I'm not on anybody's channel. I'm more of the person that is developing uh, mathematical algorithms and developing computer models, computer simulations that actually predict the weather and do projections on what the weather will be like for the next, 14 days, right? Now, I love this particular slide because some people always say, a meteorologist is a person that studies meteors. No, not really. We don't study meteors. We actually study the weather here on Earth. All right. So what do we do to collect observations? Data is extremely important to us being able to provide observations and collect information and do, numerical simulations of what the predictions are for the next 7 days, what the forecast is going to be for the next 7 days. So we have a lot of buoy data. Buoys are these instruments that basically float on the water and just they either stay stagnant or they just float across the world, and they have instruments on them that collect data. And all of that data is sent up to a satellite and then downloaded into our databases at NOAA. We also have and that's at the top left, and at the bottom right, we have instruments at every airport in the United States. They're called ASOS sites, and we collect temperature, humidity, winds. We collect all kinds of information so that information can go into our weather prediction models. We also do a lot of balloon launches. And I have an example of what a balloon launch looks like in the next slide, but we do balloon launches at our National Weather Service sites. We have over 122 National Weather Service forecast offices across the country. Whether that be in the continental United States, but we also have offices in American Samoa, we have offices in Alaska, we have offices in Guam and Puerto Rico, all of these different places where we have offices because they're all part of the United States of America. And then finally, one of our major instruments that we use to collect information is called the weather surveillance radars. It's weather radars. We have many of these all across the country. As you can see, that big ball on the bottom right is what a weather radar looks like. And we collect this information, and I'm going to show you examples of what that looks like in the near future. All right, so let me play this video here. Let me see if it'll play. 1 second. Uh-oh. It looks like my video won't play, but I'll just talk about it. As you can see, that's a weather balloon. We took a group of students out to launch this weather balloon. These weather balloons are launched at the exact same time twice a day, all across the world, not only in the United States of America, but in places in Africa, in Europe, and all over the world. Australia, they launch balloons because we need to collect, like I said, the pulse of the planet. We need to know exactly what's going on with our planet at a particular moment in time all across the world, because all of that information is gathered and used in our weather prediction models. So this young lady is being allowed to launch the balloon, and it has a string attached to it. Down from that string, there's an instrument called a radiosonde that collects temperature, wind speeds, wind direction, humidity, all of these different measurements. And once that balloon gets to the top of the atmosphere, that balloon actually bursts, and that instrument actually comes back down to the earth and of course fall somewhere on the ground. So if you ever find one of these, you'll see that it actually has information on it. The instrument has information on it on where you should return it. So that's how we get information about the pulse of our planet. We also use satellites to get information with regards to the pulse of our planet. Now, satellites, we have multiple satellites. They're usually in certain orbits in out in space, and the orbits are called either the geostationary orbit. They can be a polar orbiting. You see those red lines really close to the Earth. Um, those red lines represent the polar orbits of that polar orbiting satellite. Now, in the U.S., we have many satellites that are out there. We have geostationary satellites that sit out about 22,000 miles above the Earth's surface. And then we have these polar orbiting satellites that are somewhere around 500 to 1,000 miles um, above the Earth's surface that orbit the Earth. And now we also have a lot of partnerships, as you can see. We aren't the only ones that have satellites in the world. You know, Japan, South Korea, India, China, France, Russia, they also have satellites. So partnering with those organizations to take the pulse of the planet, to understand what's going on at any particular given moment, and collect observations of our planet is extremely important. And I'll show you a little bit about what that actually looks like in a particular picture. So take a look at this particular image right here. This is yesterday's or the day before. No, it was yesterday's um, uh, global lightning monitoring um, full color display. And so you can only get this type of picture from a geostationary satellite because you gotta be sitting pretty far away to be able to see the entire globe. Compare if you were to put your hand up to your face right now, and you act like and ball up your fist. If you're really close to the globe, to Earth, you're only going to see a small portion of the Earth. So if I put it further away from me, I can actually see the entirety of the Earth. If your hand is the Earth, right? And so we use these geostationary satellites, and this satellite actually has a lightning mapper on it. And so that's an instrument that was developed by engineers to see where lightning is going on all across the globe. And so you're looking at mostly the white parts are the clouds, right? And those clouds show you particularly where it's raining or where there's high moisture, those different types of things. And so you're seeing the United States of America in the top upper left, and you're seeing South America in the bottom right. And you can see that there's lightning going on in South America, and there's lightning going on in Mexico and over the Atlantic Ocean. All right, so let's keep going. So this particular image really is focused on getting, just the satellite image again. This is actually supposed to be looping right now, and so I'm not exactly sure why my images aren't looping. But anyway, it's fine. These are just really our satellite pictures, focused on looking at where there's precipitation or rain events, where you could actually almost see a little bit of snow here out in Utah as well, that white area right here. This was back in April of 2021. And then compare this image. This is an image taking basically the satellite and taking pictures of the Earth versus a numerical mathematical model that I'm about to show you called the global forecast system model. This particular model actually is of the Earth, but it's also really focused on using mathematical equations to tell you where clouds are. So it actually isn't, it looks similar to the image that I was showing you before, but it's actually math. It's mathematical simulations, taking data and creating a picture of where clouds would actually be across the globe. So this actually isn't a satellite picture, but it looks exactly like a satellite picture. But it's using the data that we collect from the buoys, from the radiosondes, from the airplanes, from the different satellites, and we use mathematical equations, algorithms to develop a display like this, where you'll get a projection on where the clouds are going, where the hurricanes will actually form, right? Where the tornadoes could potentially be, where it's actually going to be raining versus snowing versus sleeting, all of those things. So math, extremely important. Being able, computer programming, extremely important. When I talked earlier about running simulations, these are the type of simulations that we develop here at NOAA. And we use those simulations to give you a forecast on what we think the weather will be for the next 7 to 14 days, right? All right, let's keep moving. Now, I want to introduce you to Science on a Sphere Explorer. That's going to be kind of our tool for the day. Now, Science on a Sphere Explorer is a flat screen version of the popular Science on a Sphere. Now, Science on a Sphere actually is a globe that you could go to many museums that have the Science on a Sphere globe, and it'll display the exact same data that this flat screen version, which is called SOS Explorer, will actually display. And I'm going to show you some of those different data sets in a moment. All right. Now, Science on a Sphere Explorer Mobile is also a tool that you can actually download to your smartphone, whether you have, Google Play or an Android smartphone versus an Apple smartphone. You can download this particular tool. I have it downloaded on my phone. You could download it right now and start to take a look at some of the different data sets on this globe that we're about to go through in a moment. And so think about, after we are done here today, think about going to the Google Play Store or Apple App Store and downloading Science on a Sphere Explorer and then basically visualizing these different data sets. Now, some of the features of Science on a Sphere Explorer are basically, it's all just touch screen. There's over 140 data sets. There's some of them are real-time data sets. There's some educational videos. If you're really interested in a particular data set, you can, do a deeper dive into that data set. There's tours that are narrated, and those different data sets will help you really make stronger connections with what's going on in our environment on Earth, right? And there's also some tools that you can analyze the different data with, plot data and create visualizations, those kind of things. It's a first person experience. It's something that I highly recommend. It's a tool that I've used for different talks, and it really is it's a very interesting and amazing tool for, learning about our Earth and our planet. Now, why do we use Science on a Sphere? Data. We need to visualize it. We need to analyze it. And data is very complex now. We all know that. The data that we use can be extremely complex. We need better ways of visualizing it and understanding it and being able to take it apart and just, look at it from different ways, right? And so data visualizations helps us really to understand what's actually going on with our Earth. It's some of it is real-time observations that are being displayed on a globe versus, the modeling that I was talking about, the computer, the numerical modeling that I was talking about. So we have observed data sets here, but we also have computer model data sets, right? And that visualization really helps you to see other things that would kind of go unnoticed, help you to see some different trends. And so I'll be asking you guys about some different trends of what you're actually seeing. And what are we actually learning from looking at this visualization? So I'll ask some of those questions really soon, and I really want you guys to be on your chat. I need to see some of your chats coming in, or else this is going to be really boring if it's just me talking the whole time, right? All right. I don't want to be the one talking the entire time. I really want to get some interaction with you out there. And so, yeah, again, big data really is an emerging trend, and having a lot of different data sets, you know, it's really important to be able to display those data sets in terms of the science that we do, in terms of how we market the science that we do. And, SOS Explorer really is a technology. It's something that was developed by some software engineers to help explain science and to help explain our world. It's a really cool tool. And I want to show you that particular tool right now. So I'm going to stop sharing my screen on this computer, and I'm going to switch to my other computer, my Science on a Sphere computer. So give me 1 second. All right. So now I'm going to share the screen over here, and I'm going to open up Science on a Sphere. And as you can see, let's see, is my screen being shared? Yes, it is. There it is. As you can see, you're just looking at my computer screen here. And I have an app on here called Science on a Sphere Explorer. Now, teachers, if any teachers are out there, you could basically get this particular tool for your classrooms as well if you actually wanted to. You just got to have a certain type of setup in order to be able to do this. All right. So now you should be able to see the globe there. All right, I'm gonna hide that. It's still loading up, and it has all of these different data sets. So there's different categories here on the left. We have air data sets, we have land data sets, we have movies, people, we have real-time data sets, snow and ice data sets, space data sets, we have tours, water. These are the different categories that your data sets can actually be part of. Now, I want to open up this first data set called air traffic. Now that data set is going to load. And then what you see here is the time, 1800 hours, which is about 6 p.m. in the evening. And you'll see all of these yellow markers, yellow lines. Now tell me what you think that is. This data set is called air traffic. What do you think those yellow lines represent? Put it in the chat. I want to see somebody put in the chat what they think these lines represent. Let's see, anybody out there could tell me what these lines represent? It's 6 in the morning. All right. What do you think the yellow lines represent, everybody? I'm waiting on a comment. All right. Well, now I'm gonna actually tell you. These yellow lines represent airplanes. These are airplanes. They're commercial airplanes that say like a Delta Airlines or a United Airlines or an American Airlines. These are private flights as well. These are cargo flights like the UPS flights or the Postal Service, those kind of flights. These are also military flights as well. So this data set contains about 87,000 flights. And so what do you all think with regards to, it's midnight here. Now notice how light, it's not as many yellow lines here now, but I'm gonna speed this up and it's gonna turn into 6 a.m. and see what happens at 6 a.m. See, it's coming from darkness to daylight. As you can see, the traffic picks up in the daylight. Now, you see flights going across the Atlantic, flights going across the Pacific. You see flights going across Canada. I don't know where these people are going, but there's people going all over the entire world. At any given moment, there's always a flight in the air. So I'm gonna go over here to Africa, and let's see what's happening in Africa. So it's 12 noon. You see some flights out in Africa. You don't see as many flights as you did in the United States of America, right? But you see a bunch going on up here. What's that country up here? Let's see. Let's put some labels on this so you can actually see the countries. You see Niger, Algeria. What are these countries up here? Norway, Sweden, Germany, France. A lot going on. And now let's zoom in to this data set here, and let's see how busy it gets. Oh, look at that. It explodes with tons of air traffic during the daytime over Germany, over Romania, over France, over the United Kingdom. Plenty of flights going across Europe. Now it's turning into night. Let's see if it slows down. See if the air traffic slows down at night over Germany. Still fairly busy. Now it's starting to slow down. Not as many flights going on at nighttime over Germany now. But again, it's starting to pick back up, of course, during the daytime. All right. So let's keep moving across the world. I'm going to zoom back out a little bit. Plenty of flights going across Russia. Let's see, what else? Okay, let's look at China. A lot going into China as well. Slows down at night again. But as you can see, this is midnight. Let's see if it picks up during the daylight. Yeah, totally picks up during the daylight here in China. Also in Japan, flights going from China to Japan. As you can see, it's flights coming from everywhere. Australia, let's go into the southern hemisphere. It's nighttime in Australia now. It's almost midnight coming around in Australia. Now daylight is about to come. Let's see if the flight traffic picks up in Australia here. It does, but Australia really has mainly two areas, one or two to three areas here. Never been to Australia, but it's one place that I want to go. So one of these days I'll be on one of these flights going to Australia. Now let's take a look at another data set. All right, the next data set I want to show you is called human transportation. Let me see if I can find it here. There it is. Now, take a look at all of these different lines. In this data set, it actually shows you that all of the red lines, there's over 87,000 red lines that represent the daily flights that are going on each and every day. The blue lines represent commercial vessels, which are basically ships, over the course of a year. And then the green lines represent the world's roads that are used by over 1 billion motor vehicles. So let's start to take a look at the United States. Let's get some borders there and add the country names. And so let's go to the United States. There's Hawaii right there. As you can see, these blue lines pretty much transect the entirety of the Pacific Ocean. So I don't know exactly whether they're going from east to west or west to east. It really doesn't matter. But you can see that there are commercial vehicles going from China all the way over to the United States, down into Panama, of course, going into Mexico. And so many of the blue lines represent, of course, our ocean traffic. And we also collect data from ocean ships. A lot of the ocean ships actually have data on them as well. And so you can see that many of the products that come from the ocean, come off the ocean, aren't necessarily made here in the United States of America, right? You could see us probably, producing products that go to China or Japan, and then China or Japan also produces products that come here to the United States of America. And so these red lines, of course, are mostly, you'll see most of the red lines, especially the busyness of the red lines over land. So those represent your flights each and every day, right? All right. So let's take a quicker zoom in a little bit, and you'll see some of the green lines here in Mexico. It's a little bit easier to see the green lines in Mexico. And again, those are your roads. It said that over 1 billion cars drive our roads each and every year. All right, is there anything else anyone wants to see on this one? Let's keep going over the Atlantic. Look at that. All of the different blue lines out there, all of the different ships, and the red lines representing the planes that are going, from the United States or North America out over into Spain or different places, Morocco. It's pretty red over Europe, right? So a lot of flights, remember in our air traffic one, a lot of flights over Europe compared to not as many flights over Africa. You see the red really kind of slows down over Africa. And of course, the blue stays over the ocean because those are your ships traveling. Look how busy it is over China, all of the red over China. And the roads, you don't see as many roads in certain places. You don't see as much green in certain places out here over China either. But you see a lot of red going with the major cities that are in China, and of course Japan as well. All right, so that's our human transportation. Now let's transition to taking a look. Let's go back to satellites, and I want to show you a couple of data sets on satellites. Let's talk about we talked about the geostationary satellites versus the polar orbiting satellites, right? You guys should remember that. And let's take a look at some of these satellites in their orbits. The satellite positions data set is what this one is called. Let's zoom, look at that. Remember, what are the yellow ones that are just basically moving? They're really close. These are different names of satellites. And again, I said that all of these satellites are not owned by the United States. Many of them are owned by different countries. I'm going to speed this up so that you'll see the number of polar orbiting satellites that we have out there. I can zoom in here, and you'll be able to see how these satellites really do move across the Earth. And again, they're so close that they're only being able to see a certain part of the Earth, right? But when you zoom out, you'll see that there's geostationary satellites out here as well. You see that GOES, geostationary orbiting satellites. GOES 17 is one of the NOAA satellites that we own. You can see they're much further away. Again, over 22,000 miles away compared to some of the polar orbiting satellites being maybe 500 miles away from the Earth's surface. So you're going to be able to, from our GO satellite, you're going to be able to see a bigger picture. You're going to be able to create those big blue marble pictures that I was showing earlier. So as you can see, a ton of satellites out here, not all of them that the United States owns. And then these GPS, those are global positioning satellites. So in order for us to get our GPS data out there, we're able to show you guys and how many GPS satellites that we actually have out there in space. So this is pretty cool, right? So this gets a chance to show you how we create the images that we create with regards to, you know, the blue marble satellite, the clouds. I'm gonna show you a hurricane simulation in a minute here. So this is a really cool data set. This is a really cool tool. Let's talk about space trash. Now, space trash, there's a lot of satellites out there. There's a lot of debris out there. As you can see, these brown markers represent the different satellites that are out there. We have NOAA satellites, active satellites, we have inactive satellites, and we also have debris. So I'm going to turn off the NOAA satellites, the active satellites, and the inactive. As you can see, now it's only displaying debris. All of this debris out there in space is called space trash, right? Ton of debris out there. Now let's just put the NOAA satellites on. NOAA satellites are probably going to mainly focus on looking at the United States, correct? So let's see where some NOAA satellites are. There goes one NOAA satellite right there. Another NOAA satellite out here. Got satellites, NOAA satellites over Africa as well. Now let's add some more active satellites. You see those brown spots. These are probably some of the polar orbiter satellites that are being shown here. And then if we put inactive, there's a lot of inactive satellites out there. You see the debris really jump up with regards to the different satellites that are out there that are inactive compared to the active. It's definitely a big difference. All right, next one I want to go to is I want to show you a couple of what does it look like when the satellites actually take data. Let's take a look at some of the hurricane information. Let's take a look at the hurricane season in 2020 data set here. Again, these are your clouds. That's Africa. Anybody know where hurricanes form? Now we're over the Atlantic. Let's see how many hurricanes you all can spot in this particular data set. This data set starts, I think, in May of 2020. Let's speed it up so it'll go a little bit faster. Now, in 2020, pretty busy hurricane season. You'll see names pop up. Tropical Storm Cristobal popped up there. We had 31 tropical depressions, one of the busiest seasons on record. 31 tropical depressions tied a record with the year 2005. Now, we actually had 30 tropical storms. So that T.S that you see, TS Faye, that means Tropical Storm Faye. Those Tropical Storm Gonzalo, Hurricane Hannah, the difference between a tropical storm and a hurricane is how it's rated, how much wind speed, how fast are the winds with regards to a hurricane. Now, a tropical storm is basically a hurricane is a tropical storm with winds that have reached a speed of 74 miles per hour or more. So in order to be considered a hurricane, your wind speeds have to be higher than 74 miles per hour. If you're below that, then you're a tropical storm. So anything I think above 30, 37, 38 miles per hour is considered a tropical storm. Now, how do they form? Now, hurricanes form when there is moist air and over water, and that moist air begins to rise. That moist air, that rising air, is replaced by cooler air. Okay, the temperature of that air decreases significantly. And this process creates all of these large cloud systems. Now, everyone should know that the Earth does rotate, correct? And with the rotation of the Earth, that creates what we call a Coriolis effect. And so it allows those hurricanes to actually start to spin because the Earth rotates. Now, many of our hurricanes, they do form in the Atlantic region. As you'll see, I'm looking here over the Atlantic area. You see many of our hurricanes start to form off the coast of Africa as well. You see, this is part of the equator or just around the equator. And you see many of our cloud systems coming off the coast of Africa. And then many of them kind of get blown away. Here goes one forming tropical storm Cristobal, goes over land. One thing you'll notice when the hurricane goes over land, it kind of falls apart. Why is that? Because it doesn't have the moist ocean to energize it. It doesn't have its energy source anymore when it goes over land. Now, again, we have 14 hurricanes in 2020. We had 7 major hurricanes. Now, a major hurricane is defined as anything category 3 or above. Now, this number 7 actually tied a record high with 2005. So 2020 compared to 2005, pretty similar in terms of hurricanes, the number of hurricanes and the impact of hurricanes during that particular year, during those 2 particular years. All right, so let's take a look at one more hurricane simulation, and we'll just take a look at, maybe everybody has probably heard of Hurricane Sandy. Hurricane Sandy occurred in 2012. So this simulation starts in October 22nd, 2012. Let's see if we can identify when Hurricane Sandy forms. You can see something coming right here. Take a look be able to track that system there. It's off the coast of Carolinas. Now it's off the coast, the mid-Atlantic coast, and actually moves west. That was Hurricane Sandy right there. And Hurricane Sandy brought a lot of coastal inundation, meaning a lot of water being pushed from the ocean into the New York City, New Jersey area. You can see it form out here over the Caribbean. It stays off the coast. It's not very well formed right now. You can still see the spinning structure there. But the funny part about Hurricane Sandy is that it moved left, it moved west, and caused a lot of damage in New York City. All right, it's about 11:53 in Colorado, so somewhere around 1:53 for you guys on the East Coast. And I want to show you one last data set. And this data set is Facebook connections. It's called actually Facebook friendships. So in this particular data set, each of these blue lines represents 10 million Facebook friendship pairs across the world. Now, you'll see here, the United States is pretty bright in white here, shows how connected we are. But then as you go over the ocean, you'll see all of these dark blue lines, light blue lines going out. So people, showing their different connections, many connections in the United States, but not only in the United States, but connections going from the United States all the way out to Hawaii, connections from the United States going down to parts of South America, connections in the United States going um, across the Pacific into Asia. And you'll see many of the connections, the stronger connections are the darker the blue it is, or the lighter the blue it is, excuse me, you'll see there's many more connections in these particular areas. So many of the connections are regional, but then when you look at the globe as a whole, you'll see so many different lines spanning, going across the ocean all the way into the United States, going across the ocean into Europe, into Africa. And so when you think about the connectivity of the world, think about, are we a global society, right? And the answer that you have to say is absolutely. You look at the human transportation, it's easy for us to fly anywhere in the world now compared to, the 1950s or 1960s or pre-internet. The connections that we have, today, it creates a much smaller world and a more connected world. And so I just wanted to share that with you all. I hope you enjoyed the presentation today of Science on the Sphere Explorer. I hope it was interesting and you learned something new. Remember to download it if you have a Android or a Apple smartphone. You're welcome to download the system and play with some of these different data sets yourself. So Carlin, I'm gonna turn it back over to you.
All righty, we just have one question for you before we wrap up. And that is, so you mentioned in your presentation that a lot of your work has been with creating mathematical models, correct? So can you talk about how those mathematical models got transformed into those vivid images that we saw?
Yeah, I could talk a little bit about that. You think about you take mathematical equations and you code them. You basically put them into kind of create turn the math equation into a coded equation, meaning most of our models are written in a programming language called Fortran. So Fortran is a great language for taking math and interpreting it into a coded language. And so those coded languages, now we take data and we put values for X and Y into the coded program. So we take the data from, say, the radiosine and we put it into these mathematical formulas. And then those formulas, we do calculations. It's similar to what you would do on your phone. We put those or into your calculator. We put those equations into a computer program, and that computer program basically produces an output. And that output usually is like I showed earlier. It can be cloud information, and we integrate those. We take that information and display it in a way where it actually produces something real that we can actually see, like a cloud, right? And so it goes from taking the observations to inputting that observations into an equation that basically is a programming language. And then that programming language basically integrates, and we do some type of mathematical kind of future integration and saying, hey, using this equation, what's the temperature going to be 6 hours from now? taking that data that we just collected. What's the temperature 6 hours from now? What's the temperature 12 hours from now? What's the temperature 24 or 240 hours from now, 10 days from now? And we can take that information and then now display it on a globe. And that's really how we basically develop a lot of these different visualizations that you're seeing.
That's amazing. I can really appreciate that response for the youth that are watching or will be watching the replay, because I think that they might be surprised to find that when we talk about earth and environmental science, there's actually, as you described from this presentation, mathematical aspects that go into it and technological aspects into it. You mentioned how big data is a emerging trend that is also related to this work. And so one last question.
Yeah.
What would be your words of advice for future meteorologists?
Oh, well, future meteorologists, the one thing that I've learned about being a meteorologist, that you have to really be a jack of all trades. So, whether it be physics, chemistry, biology, dynamics, math, there's tons of courses that you have to take in order to be a meteorologist. So you're very well-rounded with regards to science, for sure, because you've taken so many different types of science in order to become a meteorologist. And then you're really proficient with regards to computers. We use computers and visualizations. The forecasters at the National Weather Service, they're sitting at their desk right now looking at these types of visualizations so that they can do a prediction for, or a write-up to tell you, hey, it's going to be, snowing, 2 days from now. And they use this data from the numerical models as guidance for that prediction. And so, if I'm a young meteorologist, I'm thinking about all of those things. I'm thinking about how to improve my scientific and math skills. I'm thinking about how I can volunteer and practice being a meteorologist. There's plenty of websites out there. We give out all of our modeling data for free. So people across the world use our model data for guidance for their own countries. And so start to take a look at it. Think about volunteering or joining the American Meteorological Society in one of their chapters and learn from other meteorologists that are out there. We have chapters all across the country. The American Meteorological Society is a fantastic organization, and being a part of those, you need to be a part of the community in order to learn more about what it takes to be a meteorologist and all of the things that you need to learn in order to be a meteorologist. And me personally, I love being a meteorologist because it impacts people's day. The weather impacts people's day each and every day. It's something that you have to actually pay attention to, whether it be severe weather or whether it be a bright and blue sunny skies. You want to know what the weather is going to be because it's going to impact how you walk outside, how you go to school, how you go to work, all of those things. So I love meteorology because it absolutely is one of those sciences that people have to take seriously, and it's practical. People use it every day. That part I love.
Well, thank you so much, Dr. Carlis.
Thank you for inviting me.
One question. You said join the American Meteorological Society. So do they have chapters for like pre-college students, or this is what you do as soon as you get on a college campus, join a chapter?
So their chapters are basically for anyone. You don't have to be in college to join a AMS chapter. Usually they are founded at colleges, though. So typically you'll find them at colleges, but you don't have to be. There's people that are part of AMS chapters that are professionals, that are in college, high school, and beyond. So you don't have to be, you just definitely need to find one close to you so that you can actually attend some of the meetings. And nowadays you could probably join any of them because where everything is virtual now.
Mm. Thank you. I didn't know that, so I'm glad I asked that.
Yeah.
Well, thank you so much for giving of your time, and your energy and your passion. And this is why we have STEM in the city, right? Because weather does impact. I'm about to go to the grocery store, and I'm like, what do I need to put on when I head out, right?
Do I need my
And so
jacket? Do I need my
that
umbrella?
yeah, and so this is the exact reason why we have the STEM in the City workshop, right? So we can make that connection to how STEM impacts our everyday lives.
Yeah.
So thank you so much for teaching us. And I downloaded the app during I don't know if
Oh,
I'm going to use it, but I
awesome.
downloaded it.
It's just something
uh,
you can play with and show people. To me, it's a conversation starter too. So you go to a nice little event and you're like, "Hey, you ever heard of Science on the Sphere? Let me show you something here. Check this out."
Yeah. So again, thank you everyone for tuning in. Thank you, Carlis, Dr. Carlis, so much for sharing that tool and reminding us the importance of your work as a meteorologist and how it impacts our everyday lives. Thank you everyone for tuning in, and thank you, Carlin. And we look forward to seeing you all at our next STEM in the City workshop.
Thank you.
All right, goodbye.
Bye.